Okay, so I'm in Xcode, so this is going to be about code, because partly what this project is about, Plink, Plonk was about having a framework for not only prototyping work, prototyping applications, prototyping interfaces, but also to then take that forward so it's scalable to be able to then actually release an application with it without having to go through an extra step of then redoing it and starting again. There's chainsaw technique that you might have to have, or something like Ensign Audio, which is an interesting project taking PD patches and then turning those into code. But this was about having an end-to-end system so you could prototype things quickly, but also then be able to use it for applications. It's also for teaching as well. Teach at the University of West of England, so partly about using that to teach students to create audio software, and I've got a couple of examples of that as well. So, I'm not using PowerPoint, I've decided to use Xcode to do the presentation, so I've got little drop downs here. I'll put this and link to it on the Twitter feed for the conference as well. Okay, so I've talked a little bit about what the project's about, but basically how I arrived at it was that I used to be a Supercollider user. I do use that in the past tense. Many of you have come across Supercollider, and I think it was just the look and feel of the language was so easy to create simple things, but then also to take it forward to make complex projects for performance, live coding, and that sort of thing. So one of my first kind of outings was when I thought, well, you could just do this in C++. So I made a system called UGen++, which basically used a lot of the codes from Supercollider and created a project that would do the same sort of things that you could do in Supercollider, but you were actually writing C++ code. I didn't really think it was going to work, so I didn't really expect it to get as far as it did in terms of it working. I think someone's taking it and turned it into an OFX module somewhere in Open Frameworks. I don't think it's used by many people, but I have seen it somewhere on some of the Open Frameworks links. But there were some problems with that. And also you might be thinking, well, why don't you just use one of the ones that already exists? There's Software Development, Software Synthesis Toolkit, and Karma. There's Sundobj, there's RTCMix, there's Sizzle at Create, there's Clam, there's ... there's loads, there's Maximilian at Goldsmiths. There's all sorts of things. I think it was because I liked the way in which you could construct not only the synthesis systems, the audio processing system, the Supercollider, that many of these systems work in a slightly different way. And actually, Jamie and I wrote a paper a few years ago that reviewed a number of these frameworks from varying perspectives in terms of using them for teaching, research, and also for further development. There's a link there to the paper on the AES Electronic Library. So I created UGen++ based on Supercollider. What did I learn from that, and what went well and what didn't go well? Well, the things that worked well was that I managed to get it to work multi-platform without too much difficulty. That was partly through using Juice, which we'll come back to shortly. The memory management model that I used was to effectively, programmers amongst us use reference counting. So each object that's created, each oscillator, or each whatever it is reference counted, so that memory is effectively managed automatically. I use the same methods of graph construction. So how do you connect an oscillator to a filter to the output? How do you connect a whole bunch of things and mix them down? Those kinds of issues, how does that work? Let's say I use the same model as Supercollider and managed to get that working in C++ syntax. Again, the other thing I borrowed from Supercollider in C++ was in UGen++ was the multi-channel expansion. So the fact that you could put a multi-channel thing into an input, and that thing itself automatically becomes multi-channel. So if you have multi-channel sine wave oscillators and put them into something, then that modulator automatically becomes multi-channel. Okay, what didn't work well? Well, the main thing, and this is deliberately the first one in the list, was the GPL license. And the fact that those of you who know James McCartney, the author of Supercollider, he's also fairly stringent about how he would come after you if you didn't stick to the GPL license. Why is that an issue? Well, I wanted to make an iOS app, and people probably have. There's the VLC app that's been up and down on the App Store that's with the GPL license. but it's just too risky to expect other people to perhaps risk the Supercollider license. So I wanted to use a different license, so that's why I started again. The other thing that I wanted to perhaps explore was not being limited to using floating point types. MaxMSP, we use 32-bit floats. A lot of DAWs use 32-bit floats. We're also beginning to see higher precision processing, and also at the time when I was starting this, then iPhones their default format was integer formats. So could we have a system that would do all of these formats as well by starting from scratch? There are also some issues with multi-threading, so communication between the GUI thread and the audio thread was effectively using mutex locks, which programmers will know you perhaps shouldn't be doing in audio code. So I wanted to look for lock-free solutions. There's also a strong dependency on Juice, because partly another reason for developing UGen++ was for teaching an MSc program at the university. So those are the things that I wanted to kind of keep, and some of the things I wanted to fix or get rid of. So what are the other things I wanted to do? Well, I wanted to support the different sample types, as I said, have a liberal license, so it's under a BSD type license. I wanted it to be easy for prototyping, like I mentioned earlier, but I wanted to be able to then take those prototypes and be easily scalable to make them into full and releasable applications. Keep the multi-platform aspect, so Mac, Windows, iOS, possibly Android, and so on. And also to have minimal external dependencies. So although the examples I'm going to show today are using the Juice framework, you're not fully locked down to using Juice. I mentioned some of the things along the way that are kind of optional and that you can do things in different ways. In terms of audio features, then what have we got? Well, some basic oscillators, sine wave, sawtooth wave, noise, that sort of thing. All the filters you'd expect to find, low pass, high pass, resonant low pass, peaking EQs, band pass, and so on. Wanted to be able to do arbitrary arithmetic on signals, very much like you can do in MaxMSP, so you can connect just two signals to add them together, or to multiply them, or to divide them if you want to get glitch stuff, as we did in the late 90s and early 2000s. And I won't subject the Gen X to any more of that. I see that their red lights have been flashing quite a bit today. Audio file reading. One of the first things I wanted to be able to do was to be able to play files. Again, looking at licenses, there's probably a few more things out there now, but the lib sound file library is fairly popular, but that's also GPL or LGPL, so there was an issue. And there was a few other things out there, but I decided to, partly as an academic exercise and to teach myself how file formats work, I basically wrote all the file format stuff myself from scratch. Other stuff in there, FFTs, and more recently I've just put a real-time partition convolution process in there as well. And also in terms of taking the scalability factor, so taking it to actual applications, then obviously we need to be able to optimize things to make it as efficient as possible. So using optimized vector routines on Apple, then on a Mac and iOS. You can use the VDSP routines to speed up things, so you can use the SIMD calculations. And more recently I found implemented the Intel, whatever IPP stands for, performance primitives, that do the same sort of things, but on both Mac and Windows. The other thing I wanted was no need to have a fixed global control rate, like Supercollider and many of the other Music N type languages have, in that you can implement that by having arbitrary block sizes and a related sample rate that corresponds with that block size. So, how do you do some things? Well, in getting started with a project, I wanted it also to be really easy to be able to start a simple project without having to check all sorts of header includes and so on. So effectively, although that and is in the wrong place, we just want to be able to drag some folders into a project and make it work. So if I just make a new project in Xcode, for example, I'm just going to do a command line app that's just basically just going to take a buffer of samples and write it out to an audio file. So just create a blank project. And then here's the repository for Plonk, Plink, Plonk, Plonk, and effectively we just need these 3 folders here: Plonk, Plink, Plonk. It was also the type of music I was making at the time, Plinky, Plonky music. So to add them to the project, make sure we add target. Okay, so there we have, this is Xcode template. I'm just going to copy and paste the code from the example that I prepared. But other than that, it's a completely plain project created by Xcode. So the only thing we need to include is the Plonk header. And effectively just a few things that might be useful to know. This is basically an array. So we've got float, floats plural. I quite like using plurals in code as a kind of interaction with the software. So that's an array of floats basically. There's going to be a buffer. So I've got some things that can create useful stuff like a sine wave. So here we're going to have an 8,192 point sine wave. I've made my own file path class, but if I was using Juice, which we'll look at in the later example, then I'd probably just use its built-in file navigation stuff. But this is one of those examples where I wanted to have minimal dependencies. So what this says is get the user's desktop, and then get a folder, get a file on the desktop. Because I might have been running this earlier while I was in the audience, I just wanted to make sure I wasn't going to fail when it tried to write a file that's already there. So this just will delete the file if it already exists. And then here's some more Plonk code. Basically, I've got the audio file writer, and it's a templated class. So you say, well, what sort of samples do you want to write? So that could be a short, if you wanted to write 16-bit audio. If you were writing, I can write org vorbis files. That's one of those dependencies that I have got in Plonk, if you want to use org vorbis, but it's optional. But one of the things I've done, which is similar to the way that Juice does it, is that actually all the source code's included, because again the license is compatible with what I've issued Plonk with. So this could be pretty much any type, as long as the file that you'd end up with is a valid audio file and you're able to load it into whatever application you want to load it into. So I've got the file name, or file path rather, it's a full file path. How many channels? Well, actually it's not just number of channels, that's actually channel layout. So looking at the WAV file format, it includes all of the abilities to say, well, I've got the left channel, the left surround channel, the right surround channel, the center channel, and all those sorts of things. So this could be more, if this is bigger than a certain value, then it's actually a code to say what channels have I got available. But if you're just using small numbers, it's basically how many channels is there. And then we've got the sample rate. And then it just takes that buffer and it writes those frames to the buffer. Now this could be, in a real application, you could be repeatedly calling this, so taking some samples in and piping it out to a file. But in this case, it's just going to take these samples and write it out to a WAV file. All those warnings are org vorbis, not me. Which I could fix, probably, but... Okay, so finished. So we should have on the desktop output WAV. Whoa, I made a sine wave! What an accomplishment. Jamie's often complimenting me on how many sine waves I can create. Because one of my metrics was, well, how many can I do at once? And I think I managed to get it to do more sine waves than Supercollider at once. And Jamie tweeted, well done. Something like that. Okay, so that's just a simple example. So this is used doing it offline. So for example, one thing that this has been used for recently, I had a student who did an internship with a hearing aid company, and they were looking to oralize people's audiograms. So they'd have a series of sliders on a web page, and they could put an audiogram in, and they could say, well, this is what it sounds like for this person. And one of the things they were using was the Web Audio API to do the filtering. And there's something about the filters, particularly probably because the phase of the filters, that doesn't quite produce the result that you'd expect to hear. And we think that what probably is the issue is that we should be using more linear phase filters. So the student used Plonk to create some impulse responses, just using a few lines of code to then be able to use that using convolution instead, to have the linear phase FIR filters instead. So you could just have simple applications like this, not necessarily something interactive. Okay, so let's collapse that one. So simple real-time usage. Effectively, one of the easiest ways of doing it is to use Plonk as a juice module. So effectively, this folder within the tree here, you can just tell juice that is a juice module, and it will automatically be included in its project management tool called the introducer. So this is the introducer here. We've seen a few apps that look like they've been juiced today. We've been spotting which look and feel people have been using in the audience. So these are built-in juice modules for doing various things, and there's Plonk at the bottom. You just tell it that's where the folder is, and it will include the code automatically. And then we just need to inherit from one of these classes that will act as an audio host, so a thing that will interface with the audio hardware. And then we need to just at least implement one function, and this one here, construct graph. So the thing that's got all the wirings between oscillators and filters and envelopes and whatever you've got going, you can return that, and that's the thing it will play. So some simple examples of this. Well, the one we've got that I tested it with at the beginning of the session to check audio was working was this here. So just a simple sine wave. So if we have a sine object, this is going to create an audio rate sine. So here's some kind of legacy from working with Supercollider and Music N type languages. And then we've got a bunch of arguments. This is, you can probably guess, is frequency, and this is amplitude. I'll just run it. You already know what a sine wave sounds like, but I'll run it to check that it works. So there's a kind of minimal prototyping type application. So we're inheriting from the Juice audio host. This is a Juice class. The component says it's actually the window that we're not actually using in this case that pops up. That happens to be its size. So in fact, the only two lines of Plonk code here are the thing to start the host, start playing the audio, and to return the sine wave. So it's not quite as minimal as doing the same sort of thing in Supercollider. Which would be just one line, pretty much the same thing. But nevertheless, for C++ code, it's pretty minimal. So just a couple more examples in terms of how do we go on from just making one sine wave, how do we do 600 sine waves? Well, first of all, let's look at modulation. So effectively, each thing that creates audio is known as a unit within Plonk. Effectively, a unit is an array of channels. In this case, we're just using an array of one, but ultimately everything's an array of channels. So here I'm creating one sine wave. I knew I should have checked the highlight color. So we've got a 5 Hz, an offset of a scale of 100, and an offset of 440. So effectively, we've got some kind of very deep vibrato here as we're plugging this modulator into the frequency input. So previously, we just had a constant here, and very similar to the way in which Supercollider would work, because you could put a constant in or something that changes. So you're using this unit generator model within this system. Again, we're just using a constant level. So here we should just have quite a wide vibrato at 5 Hz. Okay, so what other things might you want to do? Moving on. Well, multi-channel. As I mentioned earlier, by effectively putting in an array into our input here rather than just a single constant, this is actually using C++ 11 syntax. You can't do this earlier, but it was something that just kind of magically worked in Plonk when C++ 11 came out. So here we're going to have 800 on the left, and if we're getting anything above 1000 Hz on the right, still, then we'll have 1000 on the right, especially if they're wired the right way around. Yeah, that's probably working. Okay, so we can take that even further. As I said, multi-channel expansion in Supercollider, and borrowing that technique here in Plonk and UGen++. here we can have our modulator going to be multi-channel. So I've got vibrato with our modulator with around 5 Hz, but slightly slower on one side than the other, slightly deeper on one side than the other, and at a different center frequency on one side compared to the other. So we've got the rate as multi-channel, the depth as multi-channel, and the frequency as multi-channel. But by the time it gets plugged into the carrier wave, it's just one thing. But automatically inside it will then expand that to put a 4.4 rate vibrato with a depth of 100 at a center frequency of 440 on that side, and then the other ones on that side, which I'm not going to recite. You can see the columns. So there we've got multi-channel automatically. And of course we don't necessarily need to type in all the values that we want, so we can use standard programming constructs, loops and so on to create things. In this case, I'm actually using the float class within Plonk to create an exponentially distributed random series of numbers between 100 and 1000, and I'm going to make n of them, and I've just stuck n in a variable up here because I need to scale it down. And here's another class, mixer. So if you put something that can be mixed, that can either be a unit that's already multi-channel, or it can be an array of units that need mixing down. That will take all of those, mix them down. I'm just scaling it down here so that it's not going to clip. And this is running in debug mode, so it's not optimized. It glitched when I put it on 100 earlier, but if we were running optimized in release mode, then, as I say, you can do 600 or something like that. So that's using arrays. There are filters, as I mentioned earlier, so here's just a quick filter example. Oops, just copied it again. So it's a filter being modulated, so white noise this time, so another oscillator. And using a sine wave for the modulator, a slow one this time, so we're going to have a kind of wind type soundscape. Linear to exponential mapping, so that we've got our frequencies between 50 and 10,000 Hertz. And there's a filter, RLPF, resonant low pass filter. I think we only need one of those, but it would keep doing it again. So those are some simple examples. In my 1 and whatever minutes it is remaining, one of the reasons for using Juice is that it's really straightforward for making user interfaces that again can be scalable to full applications. We've seen some of those applications today, not least Glover, for example. So this one's just a simple one that creates a slider. This is the slider stuff. And I'm just going to control the level of that slider, level of the sine wave using the slider. Oops, I knew I should have set the limit to 1 or 0.1, something like that. So again, we only need one of those. Triggering and switching, so this one will actually play sound files, so it's a sound file example. So we've got 2 buttons. You click one button and it will play one sound file, and the other button will play 2 sound files. And actually one of the important bits about this in my 25 seconds remaining is that it's this patch UGen here, in that this can be switched. So this is one of the things that makes things scalable, in that although in simple examples you can just return a sine wave, or a modulated sine wave, or a bunch of sine waves mixed together, with a patch you can repatch things in real time, and it will also do it without glitching. So it does a little micro crossfade, very much like you'll find in things like Pro Tools and so on. Okay, so my original example was switching between white noise and sine wave, and for my finale, I guess, switch between the 2 sound files. So, finally, some examples that it's been used for. Archivist Brass app I used to prototype it and develop it. Prototype some commercial apps and plugins at the moment. I've also created PAE engine, which is an Objective-C wrapper around it. So inside it's doing Plonk stuff, but we're using it to teach students Objective-C at UE. So they learn the standard UI kit stuff in Objective-C, and then they can use similar constructs using PAE engine. And that's it. There's some details there, but I'll tweet this project to the Symposium's Twitter account. And any questions, get in touch.